In this section, we're going to look at a series combination of a resistor, a capacitor, and an inductor connected to an AC source. So a series combination of a resistor, an inductor, and a capacitor connected to an AC source, okay. So we're going to look at a circuit like this. This would be the AC source, and then we have a series combination of a resistor identified by its resistance, an inductor identified by its inductance, and a capacitor identified by its capacitance. Okay, so in this section we're going to study the properties of this kind of a circuit. But before we start dealing with circuits, we're going to look at a rotor diagram, which will help us to study the properties of this circuit. So let me start by discussing a rotor diagram. A rotor diagram is basically a rotating vector that helps you to represent an AC signal. This is a rotating vector used to represent an AC signal. Suppose you have the signal V equals amplitude times the sine of omega t. Okay, this can be represented by a vector of length capital V, the amplitude, rotating with an angular velocity omega. Okay, this can be represented as the vertical component of a vector of length A, or an arrow you can say, of length V, the amplitude, rotating with an angular speed or angular frequency omega. Okay, so let's say we have this coordinate system over here. Let's say we have this vector whose length is capital V, the amplitude of the signal, rotating with angular velocity omega. So assuming started from 0 over here, this angle will be omega t. Okay, then this component over here, you see, is the hypotenuse V times the sine of omega t. Okay, so you see, you got this vector rotating. Its vertical component will always represent the signal V sine omega t. Okay, so we can represent this signal as the vertical component of a vector rotating with angular velocity omega. Now we see how we can identify the phase shift between two signals. Suppose we have V sine omega t, okay, maybe let's say plus beta 1, that's the first signal. Let me write it again. Suppose we have these two signals, V1 equals V1 sine omega t plus beta 1, and then we have another signal V2 sine omega t plus beta 2. Okay, so these two vectors can be represented as follows. We know the phase shift is beta 2 minus beta 1, right? So maybe one of the vectors is this one. So this angle will be omega t plus beta 1 for the first one, and then second rotating vector, this would be of length v1, and then we'll have another vector, let's say of length v2, and this angle over here is going to be omega t plus beta 2. So we see the difference beta 2 minus beta 1 is this angle. So the phase shift is represented by the angles between the two rotating vectors. So in a rotor diagram, the phase shift between two signals, the phase shift between two signals is represented by the angle between the rotating vectors, So you see this angle over here, is beta 2 minus beta 1, which is the phase shift in the two signals. So in the rotor diagram, the phase shift is simply the angle between the rotating vectors of the two signals. Okay? All right. Okay, with that, now let's look at the circuit. Now, since they're connected in series, they all have the same current. Okay, so since they are connected in series, the current through all the circuit elements will be the same. Okay, since they are connected in series, the current through all of them is the same. Through all of them is the same. Okay, now we're gonna represent the rotor diagram of the current on the x-axis. Okay, so this is going to be the rotor diagram for the current. This vector represents the rotating vector for the current. That's I. Okay, now we're going to look at the voltages. How about the voltage across the resistor? If you remember, for resistor, the voltage and the current are in phase. So that means the rotating vector for the voltage across the resistor and the current will be in the same line because there is no phase shift between them. Okay, so the voltage of a resistor will have a vector that rotates together with the current because there is no shift between the current and the voltage across the resistor. Okay, the phase shift between the current and the voltage across the resistor is 0, which means the two vectors are going to rotate together. How about the voltage across the inductor? We've seen that the voltage across inductor leads the current by pi over 2. So you see, so the angle between the rotating vector for the across the inductor is pi over 2 ahead of the rotating vector of the current. So if the current is on this line, obviously the rotating vector for the inductor will be over here. Okay, so this represents the rotating vector of the inductor. And for a capacitor, we've seen that the current leads the voltage across the capacitor by pi over 2, right? So if the current is on this line, then the capacitor rotating vector should be over here. This is BC. All right. Now our goal is to combine them together. So as you can see, it's going to be vector addition. Now these two are in the same line or in the same phase, so we can just add them together or subtract them together. So the net of these two would be VL minus BC. Let's say sum over here. This is VL minus BC. That is the combination of these two. And then we have the following. This is VR. This is VL minus BC, and this is the net voltage. This is the net voltage V. Okay. the net voltage V. So this is what we have. We have VR over here. We have VL minus VC over here. So we can use Pythagorean theorem to express the net amplitude V in terms of this voltage. Okay, so we have the square of the net amplitude equals VR squared plus the vertical component squared, VL minus VC squared. So we see that the net amplitude is the square root of VR squared plus VL minus VC squared. So that's how the voltages are added in a series combination of resistor, capacitor, and inductor. You remember in DC circuits it was algebraic addition, but in the case of vectors, the amplitudes are added like vectors. Okay, so in this case, V is net voltage. This is net voltage, and VR, so amplitude is voltage across the resistor. VL is voltage across the inductor, and VC is voltage across the capacitor. Okay, so that's the way voltages are added in the case of AC circuits. Now we're going to define the resistance of the series combination of this elements. It's called the impedance. It's just like the capacitive reactance of a capacitor or inductive reactance of a capacitor. The combination is called impedance. So let's define what impedance is. We're going to use impedance of a series combination. We're going to use Z to represent it. We're going to use Z. This is defined to be the ratio between the total voltage and the current in the circuit. It's basically the resistance of the circuit, the total resistance of the circuit. So it's defined to be the ratio between the net voltage, let's say the amplitudes of the net voltage and the current, net voltage and the current. That is how the total impedance of the circuit is defined. So we have Z, the impedance equals the amplitude of the net voltage divided by the current. Okay, this is the definition of the impedance of a circuit. Obviously this is volts divided by amps, so the unit is ohms. Okay, now we want to get an expression for this one in terms of the resistance, capacitive reactance, and inductive reactance. So if you remember, the voltage across the resistor is current times resistance. The voltage across inductor is inductive reactance times the current, and the voltage across the capacitor is current times capacitive reactance. Okay, so we have the following: V, that's the net voltage, equals the square root of VR squared plus VL minus VC squared, right? Now the impedance Z is V divided by the amplitude of the current. Okay, so this is the expression for the amplitude. All right, now we're going to simplify this. We're going to use these formulas to simplify this expression. So we have this equals square root of, this is current times resistance squared, and then you've got current times XL minus current times XC squared divided by the current. Now you see you've got I squared, so you can factor out I from this equation. Okay, so and that I is going to cancel this expression. All right, or if you want, you can write as I, which is over I over here, it cancels out, and then we have R squared plus XL minus XC squared. Okay, so we have an expression for the impedance. So the impedance of a series circuit, which is the total resistance of the circuit, is square root of R squared plus inductive reactance minus capacitive reactance squared. Okay, and if you remember, XL is angular frequency times inductance, XC is 1 over angular frequency times capacitance, right? So if you plug in this, we've got Z equals, which is the impedance of the circuit. This equals R squared plus the square root of omega L minus 1 over omega C squared. So this is the formula for the impedance of a series circuit, the total resistance of a series circuit. And if you want, you can also substitute omega equals 2 pi f to write it differently. Okay, with that, of course, this formula would be square root of R squared 2 pi FL minus 1 over 2 pi FC, where F is the frequency. Okay, and then of course this squared. All right, so these are just alternative forms of the formula. Okay, this gives you the total impedance of the circuit. All right, next we're going to look at the phase shift between net voltage and current. Okay, phase shift between net voltage and current. Net voltage and current. This angle is the angle between the rotating vectors of the net voltage and current. Okay, this is equal to the angle between the rotating vectors for net voltage and current. Net voltage and current. Okay, we're going to represent this angle by theta. Okay, so let it be represented by theta. It be represented by theta. Okay, so theta is the phase shift of voltage with respect to current. Theta is going to be phase shift of voltage with respect to current, with respect to current. Okay, so you can say this theta over here is the phase angle of the voltage minus the phase angle of the current. Now let's go back to the rotor diagram. You see, this is the rotating vector for the voltage. This is the rotating voltage for the current. So this is the phase shift. This is theta over here. Okay, this is our phase shift over here. Maybe let me draw this over here again. So what we have is we have the rotating vector for the net voltage V, and then we have the rotating vector for the current, maybe I over here, is the rotating voltage for the voltage, and we know that this is VR over here, and this one is VL minus VC, and this is the phase shift. Okay, so from this diagram, if you use tangent, we have tangent of theta equals the opposite divided by adjacent. Okay, so you've got this equals VL minus VC divided by VR. Okay, now we can simplify this by this is VL is current times XL, and VC is current times XC, and the voltage across the resistor is current times resistance. So you see the current cancels out, and then we have got the following formula: tangent of theta equals inductive reactance minus capacitive reactance divided by resistance, and that follows that theta equals tan inverse of XL minus XC divided by R. So that's how you calculate the phase shift of the voltage with respect to the current. Okay, and if you replace xl by omega times L and xc by 1 over omega c, we can also write this formula as, so now we can write the phase shift in terms of angular frequency as follows: theta equals tan inverse of the inductive reactance is angular frequency times inductance, and the capacitive reactance is 1 over angular frequency times capacitance divided by the resistance. Okay, so this is a formula we can use to calculate the voltage, the phase shift of voltage with respect to current. And since angular frequency is 2 pi times frequency, which is the number of cycles per second, we can also write this one as tan inverse of 2 pi fL minus 1 over 2 pi fc divided by the resistance. Okay, now we can also get an alternate formula for the phase shift. You remember our Russell diagram? We have the current vector, and we've got the amplitude of the voltage like this, and then we had this one, the amplitude of the net voltage, and then we saw this one is BL minus BC, and this one is the phase shift between voltage and current. So if you decide to use cosine, then you've got cosine of theta equals the adjacent side, the voltage across the resistor, divided by the net voltage. Okay, this implies the voltage across the resistor is the amplitude of the net voltage times the cosine of the phase shift. Okay, but we can also use this formula to calculate the phase shift, because from this formula we have theta equals cosine inverse of the voltage across the resistor divided by the net voltage. Okay, and now since VR equals current times resistance, and the net voltage is current times impedance, we can also write this formula as theta equals tan inverse of the ratio between resistance and the impedance of the circuit. Okay, so that's another way of calculating. Oh, I'm sorry, this is cosine. Let me change it. Theta equals cosine inverse of the ratio between resistance and impedance. Okay, so this is another formula we can use to calculate the phase shift. All right, now we're going to look at an example. Let's say maybe capital letter, let's say 30,000 ohm resistor, let's say, and 800 ohm, Henry inductor, and 0.25 microfarad capacitor, let's say, are connected in series, to an AC source whose voltage, let's say, varies according to the equation to the net voltage, the instantaneous value of the net voltage equals, let's say, it is 10 volts times the sine of, let's say, 100t. Okay, so we have the following. This is the AC source, and then we have a resistor, an inductor, and a capacitor connected in series. Okay, this one is R equals 30,000 ohm, and this is L equals 800 Henry, and this C equals 0.25 microfarad. Okay, and we're told that this voltage over here varies as 10 sine 100 t. Okay, so A, let's say calculate the impedance of the circuit. Calculate the impedance of the circuit. All right, so we're looking for Z, and Z is square root of R squared, and then you've got omega L 1 over omega C squared. This is the formula for the impedance that we're looking for, and we're told R is 30,000, or 3 times 10 to the power 4. How about omega? This is omega. Omega is 100. So we also know omega is 100 radians per second, right? So let's plug these numbers. So this equals square root of, we've got this is 3 times 10 to the power of 4 squared, and then we've got the angular frequency is 100 and the inductance is 800, okay, minus 1 over the frequency is 100, and then the capacitor is 0.25 times 10 to the power of -6, okay, the whole thing squared. All right, so we have, this is square root of, we have 3 times 10 to the power of 4 squared. Over here we've got 8 times 10 to the power of 4, okay, minus 1 over 0.25 is 4, okay, and then you've got 10 to the power of 4 times 10 to the power of 4, the whole thing squared. Okay, so we subtract these two, we get square root of 3 times 10 to the power of 4 squared, and then this will be 8 minus 4, 4 times 10 to the power of 4 squared. Now you can see we can factor out 10 to the power of 4, okay, so you've got 10 to the power of 4 square root of 3 squared plus 4 squared, that is 5 times 10 to the power of 4, okay, so the impedance is 5 times 10 to the power of 4 ohms. All right, now B, let's say calculate the amplitude of the current. The amplitude of the current. So in this case, we're looking for I, capital I, question mark, the amplitude of the current, and we're going to use the definition of impedance, which is Z equals V over I, or current equals net voltage divided by impedance. Okay, so we're told the net voltage has an amplitude of 10. Okay, so capital V, which is the amplitude of the voltage, is 10 volts. Okay, so the amplitude of the current is 10 volts divided by 5 times 10 to the power of 4 ohms. 5 times 10 to the power of 4 ohms. So that is 0.2 times 10 to the power of -3 amps, or we can say 2 times 10 to the power of -4 ampere, or 0.2 milliamps. So this is the amplitude of the current, right? Now C, let's calculate the phase shift. Calculate the phase shift of net voltage with respect to current. Net voltage with respect to current. With respect to current. So we're looking for theta, question mark, and we know that theta is given by tan inverse of angular frequency times inductance minus 1 over angular frequency times capacitance divided by the resistance. Okay, so this is tan inverse of the angular frequency 100 and this one is 800, okay, minus 1 over the angular frequency 100 and the capacitance is 0.25 times 10 to the power of -6 divided by the resistance, which is 3 times 10 to the power of 4. Okay, so this is tan inverse of, we've got 8 times 10 to the power of 4, and this one 1 over 0.25 is 4, so that is minus 4 times 10 to the power of 4 divided by 3 times 10 to the power of 4. Okay, so you see the 10 to the power of 4 cancels out, and so basically we have tan inverse of 4 over 3. So the phase shift of voltage with respect to current is tan inverse of 4 over 3, and that is 53 degrees. Okay, so the voltage leads the current by 53 degrees. This implies voltage or net voltage leads, because it's positive, leads the current by 53 degrees. All right. Now this is D. Let's say calculate the phase angle of the current. The phase angle of the current. Okay, so we're looking for beta I, question mark. Okay, so we have the following: theta, the phase shift, equals beta V minus beta I, and we just calculate that to be 53 degrees. 53 degrees, or if I change it to radians, it'll be times pi over 180. Okay, that'll be the angle in radians. All right, so the phase angle of the voltage is 0, because we're told it varies like this one. You see, 700t plus 0, so the phase angle of the voltage is 0. So beta V is 0. Okay, so what we have is 0 minus beta I equals this 53 degrees times pi over 180 radians. Okay, so the phase angle for the voltage is the negative of 53 degrees times pi over 180. That's in radians. Okay, all right, so that's the phase angle. Now give a formula for the instantaneous current as a function of time. So the general formula is the instantaneous current equals its amplitude sine omega t plus its phase angle. This is the general formula, but now we know all these formulas. We already calculated the amplitude of the current. The amplitude of the current is 2 times 10 to the power -4 amps. This one is 100. It has the same frequency as the voltage, and this is our phase shift. Okay, so this is the formula for the instantaneous current. The amplitude is 2 times 10 to the power -4 amps, and then we've got sine 100t, and the phase angle is minus 53 pi times 180 radians. Okay, So this is how the current varies as a function of time, right? Now let's say calculate the amplitude of the voltage across the capacitor, across the resistor. Let's start with the resistor, across the resistor. Okay, so we're looking for VR over here. Okay, and from Ohm's law, VR is simply current times resistance. Okay, so the current is 2 times 10 to the power of -4, and the resistance is 3 times 10 to the power of 4. So the voltage is 2 times 3, 6 volts. Okay, so the voltage across the resistor is 6 volts. G, let's say calculate the amplitude of the voltage across the inductor, of the voltage across the inductor. And we're looking for VL over here. Okay, but VL is current times inductive reactance. Okay, so this is current times angular frequency times the inductance. Okay, so the current is 2 times 10 to the power -4, and the angular frequency is 100, and the inductance is I think 800. Okay, so we have 2 times 8, 16 volts. Okay, H, calculate the voltage, or let's say the amplitude of the voltage across the capacitor, of the voltage across the capacitor. Okay, so we're looking at VC question mark, but we know that VC is current times capacitive reactance, right? And capacitive reactance is 1 over angular frequency times capacitance, right? Therefore, the current is 2 times 10 to the power of -4. The frequency is 100, and the capacitance is 0.25 times 10 to the power -6. Okay, so we've got this is 1 over 4, so that's going to be 8, and then you've got 10 to the power 4, that will cancel, so that's just 8 volts. All right, so that's the voltage across the capacitor. Now let's test the formula. V squared equals square root of VR squared plus VL minus VC squared. Okay, because we have all the voltages. The net voltage is 10, right? The net voltage is the amplitude of the instantaneous voltage, which is 10 volts over here. Okay, so it's over here. You see this is a signal, so its amplitude is 10. So the net voltage is 10. All right, so you've got 10 squared over here, question mark, square root of the voltage across the resistor. We just calculate to be 6, right? That is 6 squared. And then the voltage across the inductor is 16, and the voltage across the capacitor is 8. Okay, so you've got 10 squared equals, oh, that's not squared, this will be, okay, equals square root of 6 squared plus 8 squared, but this equals 10, right? So proved. All right, square root of 6 squared plus 8 squared is 10. All right, now we're going to look at resonant frequency. Resonant frequency. This is the frequency for which the current is the maximum for a given amplitude of the voltage. This is the frequency for which the current is maximum for a given amplitude of the voltage. So this is the frequency that makes the current maximum. Okay, so what the current? The current is the amplitude of voltage divided by impedance. Okay, but we just saw that the impedance is given by the following formula. Okay, R squared plus the inductive reactance, which is angular frequency times inductance, minus 1 over omega times C squared, squared. Okay, so the resonant frequency is the frequency that makes this one maximum. Okay, so you see this is a square, so this expression is maximum when this is minimum, when the denominator is minimum, but the denominator is minimum when this expression is 0. This is a constant, so the denominator is minimum when this expression is equal to 0. Okay, so we're getting this for the resonant frequency. So we have when the angular frequency equals resonant frequency, this expression should be 0. Okay, so we have the following: omega naught squared minus 1, not squared, so the whole thing squared, omega naught C should be 0. Okay, so when this frequency equals the resonant frequency, this should be 0 to make this expression maximum, right? So this is omega naught L over here. Okay, so you've got omega naught times inductance equals 1 over omega naught C. Okay, so we get omega naught squared times LC equals 1, and that gives us omega naught squared equals 1 over inductance times capacitance. So you see, we have the following formula for the resonant frequency. So the resonant frequency is square root 1 over LC. Let me write it the other side. So the expression for the resonant frequency is the square root of LC. Okay, this is the angular frequency. If we rather have the frequency, then we have omega naught equals 2 pi times the resonant frequency, and with that we get the resonant frequency equals 1 over 2 pi square root of 1 over LC. Okay, so that's how we calculate the resonant frequency. The resonant frequency depends only on the inductance and capacitance. It doesn't depend on the resistance. Okay, now you see, if you plot the current as a function of frequency, you see from this formula, if you plot this formula, you'll get something like this. This is a graph of current versus frequency. Let's say this side is the current and this axis is the frequency. You'll get something like this. It'll be something like this, where this is the resonant frequency. The resonant frequency. Okay, so the resonant frequency is the frequency for which the circuit will have the maximum possible current for a given amplitude. Now this has very important application in tuning circuits. Okay, for example, take your radio or your television. Is receiving a bunch of frequencies, but how does it know to pick a unique frequency? So when you dial your radio, you're basically dialing this frequency, okay? So when you adjust your frequency to this resonant frequencies, all the other frequencies will be cut off, you see, and you pick only this frequency, okay? So what radios and televisions have is they usually have variable capacitor, okay? So when you tune the frequency, you're basically tuning this expression over here to the desired frequency. So this has a very important application in the tuning circuits of radios, okay? You can change the resonant frequency by adjusting the capacitance using variable capacitance, and with that you can pick any frequency you want. Because if you've got a bunch of frequencies, the radio will pick only these frequencies. The other frequencies will be cut out and you receive only this frequency. That's how the radio or television discriminates between frequencies, okay? Example, let's say a radio tuning circuit let's say has let's say a series combination of, let's say, 100 ohm resistor, let's say a 2 millihenry inductor, and let's say and a variable capacitor, The question is, to what capacitance should the capacitor be dialed if the radio is to peak, let's say is to peak a signal of frequency, let's say 2 megahertz, that is 2 times the power of 6 hertz. All right, so this is the resonant frequency. Okay, this is the resonant frequency, that's the frequency when you peak. Okay, so what you have is F naught is 2 times 10 to the power of 6 hertz. Okay, and we're told the resistance 100 ohms, the inductance is 2 millihenry, that is 2 times 10 to the power of -3. So the question is, to what value should the capacitance be dialed to get this resonant frequency? Okay, so we just have to use this formula. F naught equals 1 over 2 pi, the square root of 1 over LC. Okay, so let's solve for the capacitance. We square both sides. We get F naught squared equals 1 over 4 pi squared, and then 1 over LC. Okay, so we can cross multiply. We get F naught squared times 4 pi squared times L times C equals 1. Okay, so the capacitance should be 1 over F naught squared 4 pi squared times the inductance. Okay, so the capacitance should have the following value. You've got 2 times 10 to the power of 6 squared, you've got 4 pi squared, about 40, and then you've got 2 millihenry, 10 to the power of -3. Okay, so this is about 40, so you've got 2 squared, 4 times 4, 16, that's 1 over 32. You've got 1 over 32 from the numbers over here. 2 squared is 4, you've got 4 over here is about 10, So that's 4 times 4, 16. All right, how about from the parse? We got 10 to the power of negative 12, 10 to the power of negative 13, and then we got 10 to the power of 3. So that's 10 to the power of negative 10. Okay. This is approximately 0.3, all right, approximately, times 10 to the power of negative 11. So that is, that's 10. So that is about 3 times 10 to the power negative 11, or we can say 30 times 10 to the power negative 12, or 30 picofarad. Pico is 10 to the power of negative 12. So that's the capacitance we need to tune into this radio frequency. All right, now we're going to look at what they call RMS value. RMS value. This is an abbreviation for root mean square average. Okay, it's root mean square average. This is an abbreviation for root mean square. Well, that's what it stands for, root mean square value. So it's a kind of average. It's a kind of average because if you just average this, a certain AC signal, will just get 0. Okay. So let's say we have the following signal: V equals V sine omega t. Now this function varies between positive and negative like this. So if you want to take the average of this, we'll just get 0. So what they do is they square the signal, they take the average, and then take the square root, and they call it RMS value. Okay, so you square the signal first, you get something like this, and then you take the average and take the square root. Okay, so if you've got this signal, what you call the RMS value is you square the signal, you take the average, and then take the square root. This is the definition of RMS value. Okay, this line means average. So you square the signal, you take the average, and then take the square root. That's called RMS value. Okay, so let's try to obtain expression for the RMS value that varies like this. Okay, so we have VRMS equals square root of the average of the signal is amplitude V times sine squared omega t. Okay, now this is also square, so you can factor out the amplitude. So you get amplitude and then square root of the average of sine squared of omega t. Okay, now if you remember your double angle formulas, we have the following formula. This equals 1 minus 2 cosine omega 2 wt, okay, divided by 2. Okay, now this is a cosine, still varies between positive and negative. Okay, so the average of this one can be 0. Okay, so the average of this expression is the average of half is half, but the average of this one is 0 because it varies in positive and negative. So the average of sine squared omega t is simply half. All right, so we get the following formula for the RMS value. So we have VRMS equals the amplitude and then square root of 1 over half, which means the RMS value is the amplitude of the voltage divided by root 2. Okay, so this is the average we use for AC circuits. It means root mean square. You square the signal, you take the average, and then you take the square root. Okay, now AC ammeters and voltmeters are designed to read RMS value. Okay, AC ammeters and voltmeters are designed to read RMS value. RMS value. Okay, now let's say example, if an AC voltmeter reads 120 volts, that is the voltage we get from our wall outlet, what is the amplitude of the AC signal? What is the amplitude of the AC signal? Okay, so we know this is the RMS value, so you've got VRMS because that's what ammeters read, 120. Okay, and we want to obtain the amplitude. Okay, and so from this equation, the amplitude is √2 times the RMS value. Okay, so that is √2 times 120. That is, this is about 1.4. So it's about 1.4 times 12 volts. Okay, all right. Now we're going to look at power dissipated in a series RLC circuit. Okay, this stands for resistance, inductor, and capacitance. Okay, so now you remember the formula for power. Power is rate of doing work or rate of conversion of energy. Okay, so power is well, we already defined it, but power is energy or change in energy divided by time taken. Okay, and if you remember, delta U is charge times potential difference. Okay, so we've got, this is charge times potential difference and then divided by time, but charge divided by time is current. Okay, so this is current times delta V. We have already discussed this formula in previous chapters. Okay, so for instantaneous power, if E small p, that will be current times instantaneous voltage. Okay, so this is the formula for instantaneous power, instantaneous current times instantaneous voltage. Okay, so in this case, this stands for instantaneous power. The same thing about I is instantaneous current, and V is instantaneous voltage or potential difference. Okay, so the instantaneous power is a product of the instantaneous current, instantaneous voltage. Now suppose let's say the voltage leads the current by theta. The voltage leads the current by theta. Okay, so if I equals amplitude of current sine omega t, then the voltage would be, since it leads the current, it will be the amplitude of voltage sine of omega t plus theta. Okay, so the instantaneous power P is a product of these two, I sine omega t and then times V sine omega t plus theta. Okay, but this varies with time very fast, so we need to do some kind of average. So we're going to talk about average power. Okay, so let's talk about average power. So the average power, this is simple for average, would be the average of this product over here. Okay, the average of this product over here, which is IV, amplitude of the current, amplitude of voltage, and then you've got sine omega t, and then we've got sine omega t plus theta. Okay, we have to obtain an average for this expression. So to do that, first we're going to expand this one over here. If you remember the formula for the sine of the sum of two angles, we have the following. So omega t plus theta equals sine omega t cosine of theta plus cosine of omega t times the sine of theta. Okay, so if we put that in here, we get the following expression for the average power. This would be, well, IV is a constant, we can take it out, and then we have the average of the following. We've got sine omega t, and then this expression over here, sine omega t cosine of theta plus cosine of omega t sine theta. Okay, so let's expand this. We get IV, the average of, when you multiply these two, you see you get sine squared cosine of theta. This is sine squared of omega t cosine of theta, and second term is sine cosine sine omega t cosine of omega t times the sine of theta. Okay, now what is equal to? This is half of sine of 2 omega t, this expression over here. So you can simplify like this. This is current times voltage, and then the average of sine squared of omega t using the double angle formula. This one is half of sine of 2 omega t and then times the sine of theta. Okay, now look, this is a sine function that varies between positive and negative, so its average is 0. So the average of this one is 0, and the average of sine square omega t, where so is half. Okay, so the average of this one is 0, the average of sine square omega is half, so we get the average power equals current times voltage times the average of sine square omega t, which is half, times cosine of theta. Okay, so the average power equals current times voltage divided by 2 times cosine of theta. So as you can see from here, the phase shift between voltage and current plays a very big role in how much power you get from an LC series circuit. Okay, for example, if this angle is pi over 2, cosine pi over 2 is 0, you don't get any power. Okay, so this factor over here is very important, and engineers calls it the power factor. The expression cosine of theta is called the power factor, because it determines how much power you get. So if theta equals pi over 2, no power, you get 0 power. You get maximum power when the phase shift is 0, that means the current and voltage are in phase, and you get 0 power when the phase shift is pi over 2. So the power is maximum. When theta equals 0, or when the voltage and the current are in phase. The voltage and the current are in phase. Okay, and it is 0 when the phase shift is pi over 2. The power is 0 when the phase shift is 0. When the phase is pi over 2. The phase shift is pi over 2 or 90 degrees. Therefore, it follows that since in an inductor the voltage leads the current by pi over 2, no power can be delivered by inductor. Therefore, since theta L equals 0, that's pi over 2, since theta L, put that again, since theta L as the phase shift of voltage with respect to current for an inductor is pi over 2, no power can be delivered by an inductor. No power can be delivered by an inductor. Similarly, since the phase shift of voltage with respect to current for a capacitor is negative pi over 2, no power can be delivered by a capacitor. No power can be delivered by a capacitor. But for a resistor, the phase shift is 0. But for a resistor, power can be delivered because theta R is 0. In other words, the voltage and the current are in phase in the case of a resistor. So the only circuit element that can deliver power is a resistor. No power can be delivered by an inductor or capacitor. The only circuit element that can deliver power is a resistor. Alright. So we can write it a little bit differently. We can write as I over root 2 times B over 2. Let's write this in terms of RMS values. So we have average power equals VI over 2 times cosine of theta. We can write as I over root 2 times V over root 2 times cosine of theta. But this is IRMS, this is VRMS, right? So we have this alternative formula. IRMS times VRMS times cosine of theta. So this is the expression for power in terms of RMS values. Okay. Remember the formula VR equals amplitude times cosine of theta. Okay. So you can replace this V cosine of theta by this expression over here. So you got V bar equals V, remember axis I V cosine of theta divided by 2. Okay, but this one equals voltage across the resistor. So you see the voltage across the resistor. So simply current times voltage across the resistor divided by 2. Or you can say this is IRMS times VRMS. In other words, you can obtain power only from a resistor. You can obtain power from other devices. So you can also calculate the power as simply as current in the circuit and the potential difference. This is R. Okay, so this is Lambrag like this, RMS. Okay, this is the voltage across the resistor, RMS value. Alright? Okay, so that's another way of calculating the average power. Alright. So now let's refer to the example we considered before. Sorry here. Well, let's consider the following circuit. Okay, you've got this circuit over here. We're going to consider the problem we dealt before. So this is, I think it was 3 times 10 to the power of 4 ohms resistor. Okay, and then we have the inductor, which was 800 Henry. And then we have the capacitor, which was 0.25 microfarad, that was C. Okay. Now let's calculate the power dissipated in the circuit. The question is calculate the power dissipated in the circuit. Dissipated in the circuit. Okay, so we've seen that the power equals, I'm talking about the average power, average over here, can be calculated as current times the voltage across the resistor divided by 2. Okay, and the current is amplitude of the voltage divided by the impedance. You can calculate the current using this one. Okay, and of course the voltage across the resistor is current times resistance. Okay, so you can see that the average power is the current, well, let's say half. The current is V over impedance, and then the voltage across the resistor is I times R. Okay, so this would be, this is the net voltage, okay, and this is the voltage across the resistor. So once we calculate the current over here, this is I, but this is I too, they're both I, so let's simplify it. This is I, let me put this one like this, I squared R, okay, and then that's half V over Z for the current squared times resistance. Okay, so we have to calculate the impedance first. That's all we need to calculate the power. Okay, but we already calculated the impedance, so I'm not going to do it again. We have the same numbers as before. The impedance was square root of R squared plus omega L minus 1 over omega C squared. And if you remember, our frequency in the previous problem was 100. This was V equals 10 sine 100t. Okay, so our omega is 100. If you do all that, you will see that the impedance was 5 times 10 to the power of 4 ohms. Okay, that was our impedance with these numbers. And so, well, we have also calculated the current in that problem. It was 2 times 10 to the power of negative 4 amps, right? So that's all. We have the resistance. So the average power is half current squared times resistance. So this is 1/2. This is 2 times 10 to the power of negative 4 squared times the resistance, which is 3 times 10 to the power of 4. Okay, so that's it. So the power is 1/2. 1/2 goes with 1/2. So you've got, from the numbers, you've got 3. This is negative 8, negative plus 4, negative 4. So that's times 10 to the power of negative 4 watts. Okay, so this is the amount of power, average power we get from this circuit. All right, negative 8, negative 4.